Hola. Bueno, arranquemos, ya son 6:05. Bueno, gracias a todos por venir. Esta es una de las conferencias abiertas que nos gusta hacer, especialmente cuando tenemos un visitante tan distinguido como Mario Kovač, de la Universidad de Zagreb, Croacia. Mario es una de las cabezas del proyecto EPI, EPA sería, European Processor Initiative. Es un hot topic para mí este tema, porque es diseño de hardware y es lo que nosotros les venimos contando que hagan en clase para tratar de aprovechar esta movida. Mario es uno de los principales líderes de ese proyecto y bueno, espero que lo puedan aprovechar. Es un honor para nosotros que él esté acá. Ustedes han leído la bio, si la leyeron ya saben qué clase de speaker tenemos hoy. Ok, Mario, thank you for coming. It's an honor for us to receive in our university. Now, whatever you like.
Dear Alejandro, thank you for this opportunity to have a talk here. Dear colleagues, at the beginning, I have to apologize. I don't know that much Spanish. I know a couple of words like parrilla, cerveza, and stuff like that, but this could not help me with this presentation. So unfortunately, I'll have to do it in English, but of course I will try to explain if anything is needed. To give you a little bit of background, I would like today to cover a couple of strategic European projects that are related to high-end processors. There is, I will show you some historical moments. There was quite important understanding that apart from very good developments in software ecosystems that exist in Europe, Europe was failing to provide the hardware part, the processors part for the large computer systems, and that was recognized as one of the major weaknesses in kind of both support for industry and for the research and academia. And this is when there was, I have to say, there was a political move, because unfortunately without politics you cannot start something of that importance and magnitude. There was a political decision to start rebuilding the European processor industry and ecosystem. And I will try in this presentation to give some kind of overview of how it all happened, what we have done so far, and what are some of the near future goals. So how we see that this is going to evolve in next, I would say decade or so. And I hope this will, give you at least some information, of the research. I'm personally involved, and the whole group of scientists from industry and academia in Europe are doing in this. And I would say one of the major motivations also for this talk is we would very much like to, in different ways, maybe try to include collaboration between, your researchers here and our researchers there, and see maybe we can do something even together in the future, which, of course, would be important, I would say, for both sides. I will start with first project, which was, I can say, a cornerstone of the whole development. As Alejandro just said, European Processor Initiative was this project, this first major project that was initiated. And I will give you information first, why EPI? I will try to, of course, EPI right now, just to give you information, European Processor Initiative as a project finished in March this year. There are some follow-up projects that are happening. I will talk about them as well today. But I will say what is the current status of our development, because it is important to say what happened after all these years, and give you some perspectives and outcomes. Okay, I'll start first with why EPI. As I said, Europe recognized that technological support, hardware support for the especially high-performance computing industry was quite low, and put the goal that we reach from 10% to 20% of support for this type of devices. It is still small percentage when you take a look at it. We still depend heavily on industries that are outside Europe. But if we don't start with something, this is never going to change. Second thing also is going to more advanced semiconductor nodes. So we are right now talking about development that hopefully will reach, the sizes of 2 nanometers that are, I would say, state-of-the-art today. Of course, it is important to say that we don't have foundries in Europe at this moment that could support this type of technology, and it's very expensive to build those type of foundries. But, there are some, again, initiatives to kind of enlarge some of the semiconductor foundries that exist in Europe with those more advanced nodes, and hoping that the production sizes could be larger and larger in the years to come. And of course, one of the major issues that were, when the whole thing started, that was imposed, was the recognition that the current processor architectures that existed at the time when European Processor Initiative started were no longer able to support building the exascale data centers. The exascale meaning 10 to the power of 18 floating point operations per second. Some of you may say that, yes, of course, you have, 50 racks, take 200 racks, and you can get to the exascale. This is true just kind of theoretically, because with the older type of architectures, the cost of the electric power to actually power those systems would be too large to be, first of all, from business side, exploitable. A second thing, it would be too expensive, for example, for non-commercial, like academic type of systems to be actually viable. So globally, there was a search that at that time, the search started for new types of architectures that could be significantly more energy efficient. And this was, again, good reason for Europe to say, okay, everybody is searching right now. It's not like just another, revision of the old processor. No, you need completely new approach to processors to be competitive in this new energy efficient domain. So this is a good time for Europe to maybe to try to come back into the race. So all of this was kind of initial idea that created political decision to start development of European processor. In this process, at the very beginning, as I will say, you will see mentioning of two institutions. They're called JU, as you can see in the title, which is joint undertaking, which is a kind of like, formal name for type of a company that is kind of Europe-wide. So it's not belonging to a single country. It belongs basically to, European Union type of region. And this is kind of like a special way of organizing a company. But basically what is important behind it is that, they were focused on providing support primarily by setting up the goals and providing finances for creating European HPC ecosystem, and CHIPS JU for basically improving and bringing new ideas to European chips ecosystem. When we say European Processor Initiative, what is that? This is not a company. This is not type of a university or something. It's basically consortia consisting of 27 strategically chosen companies and research institutions that were kind of compatible and also able to provide some of the knowledge that is required to create such a new type of technology. You can see that, we are from 10 different countries, and here you can have a list with logos of all of the partners that are part of this consortium. So when I said, Europe started this, it happened actually, it all started in 2017. So this is right now almost 10 years ago. This was this initial political decision that said, okay, let's try to create something technologically new in Europe. And then with that, I would not like to go with all of these details because they are not, very important for you. But, this initial movement was followed by few other both decisions and creation of Euro HPC as an institution, bringing funds from different countries, which was, of course, one of the crucial things is if you want to, create some new technology, and if you want to really kind of push it, you have to find money for that. So this was, agreed with European countries to provide partial funding for this joint undertaking, and this institution, this entity, started financing, among others, European Processor Initiative. European Processor Initiatives had two phases, like they're called phase 1 or phase 2, or formally, SGA 1 or SGA 2. I don't want to go into these legal details, but basically, those were like 3-year projects, phase 1 and phase 2. It's not, we have to be honest, it's not that before EPI, nothing was happening. There were already some projects in Europe, for example, like Mont Blanc projects that were already evaluating, some of the possible architectures, system designs that could lead to, certain new European technology for HPC, but they were really not focused on the processors itself. So the key word here was, okay, we need to really develop new processors, because when you take a look at the cost of the whole system, processors really make a large portion of that cost. And if you depend on that technology from, some third parties, then this is, of course, one of the bottlenecks that you would like somehow to resolve. So in 2019, our first phase, SGA1 started. And what is important to say is that from the very beginning, it was not yet another research project. You mean, okay, you do some research, you publish some papers, you go to some conferences, you finish with nothing concrete, okay? After 5 years, everybody forgets about it. No, the primary idea behind this was create an industrial project. So, result has to be industrial product. It has to come to the market, and then it has to have its own life, right? So you need to, first of all, design a good product. Second, you have to be sure that you'll be able, business-wise, to sustain all this development in the years to follow. Not expect that, Europe will pour money year after year after year, and nothing will come out. And third thing, which is, of course, very important, you have to look what is competition doing in the same time. And try to see that at the end, you're competing with all of the other companies that will develop their new products as well. So during the very first year of the project, there was an important milestone. Out of the project, we spin off a new company, and that company was named CPERL. Right now, probably not many of you have heard about this company, but I will show you a little bit later on in one of my slides. We all expect that CPERL will be globally quite known in years to come with the results of this project that I will show you in a couple of slides later on. So, CPERL was really one of the first key milestones that was set up so that the whole project needs to have an industrial output. What was the goal that CPERL was given? European Processor Initiative was given certain funds which were really significant, 150 million euros, to develop the technology, but not to cover all costs of bringing the product to the market. So CPERL was given a task to take this technology from the research phase, initial research phase, into the commercial phase later on, and of course cover all of the costs for this development. This is an important part because, as probably you all know, 150 million in whatever currency is a lot of money. But in semiconductor industry, especially in high-end semiconductor industry, it's peanuts. With that much money, you cannot compete with, NVIDIA, with Intel, with AMD, because, it's kind of, okay, guys, you play with those 150 millions, we'll move forward, right? So that means that with that, this was kind of like only Europe was providing the seed for this whole development. It was expecting that the industry will basically, if they want really to exploit the results, they will also bring money in and continue the development beyond the project phase. Because, as I said, taping out in most advanced nodes is expensive business. Okay, now, of course, after the initial period of 3 years, there was a second phase. The second phase, as I said, just ended end of this March. And I will show you during my presentation today what were the results of this development. I would like right now just to give you kind of like, vague time dimension of what was happening in the last 10 years with the projects. Together with EPI that was developing processors, it's very important to talk to software guys and application developers as well. Because at the end, you can have great processor, but if it doesn't fit for the applications it was built for, it's not so good. So for that part, there were like parallel projects. First of all, centers of excellence in HPC applications. There were, a lot of partners that already in the past developed, very complex, very complex applications that were running in European HPC centers. We were looking for them, and also I will show you that later on, not only that they tried to see what is kind of new architecture that we are bringing in so that they can modify their application, but also for some feedback. Also, what I will show you is in many, well, not in many, I would say continuously throughout the project, there was like a co-design process in the sense that we were analyzing what is that application needs and what is that we provide with our architecture. And with kind of analysis of what are the bottlenecks of applications today, what is it that we can provide commercially on the processing side, and how can we better adjust this. This was an important part of the design process. So to evaluate what would be good, I don't know, ratio of memory or the vector sizes or the caches or whatever is kind of one of the design choices. And what you will also see, we started 2 pilots. And the idea of pilots is that when the processors are ready, that we have a couple of systems, not kind of fully completed, but kind of like prototypes that we can use to evaluate how are we doing with those processors that we developed. And those pilots are exactly, and I will show you later on, those 2 pilots are there for a reason, because we had like 2 processor families being developed in EPI. And we are right now in 2026. As continuation, I will talk also a little bit about that today. We have project there, which is continuing development of something that was initially developed within EPI. And we have procurement of 2 large European exascale systems. And that was important because those systems will have partially our processors included, commercial version of processors included into those systems, which is confirmation of what I mentioned earlier, that we have not a research project, but we do have some industrial product as a result. So this slide gives you 10 years of our frustration, of our happiness, of our collaboration, of nights where we had sleep, nights where we didn't have sleep. So this gives you kind of short overview of all these projects that today I will talk about. Now, coming back to EPI, what are major objectives of EPI? At the core of the project, the motivation was to actually design 2 processors. No, I'm good. Thank you. One processor is general purpose one. The second processor is the accelerator for that. So we have general purpose processor and accelerator processor. Why is that? Because as we all are aware, today's computation without acceleration, well, you know, it's not that efficient, right? The old times where we had only general purpose processors are, I would say, behind us. Today, we must say that, you know, we need to have both general purpose and accelerator ones to have really an efficient system for today's application. First processor architecture, which was decided to be based on the ARM architecture, was focused for general purpose processing. Now, the question that I got quite often was, okay, so you were talking about European processors, kind of sovereignty, independence, why ARM, right? ARM is no longer European. Well, unfortunately, at the time this project was initiated and when there was an initial idea about it, ARM was still European. So UK was part of Europe. ARM was owned, you know, still by European companies. It was, you know, still kind of European. But this was not the only reason. I mean, it was, you know, one of the kind of good choices. But, you know, one of the key reasons was, okay, creating a processor from scratch, you cannot do that in 5 to 10 years time frame. I mean, you need really very long process because it's everything. From gates, from logic, from cores, from system, from all of the, you know, software stack. Then you have to have application guys, you know, accept your architecture, move to your, I mean, it's a long, long process. If we wanted to have something in a visible time frame, we said, look, there is an architecture that can be licensed, which is a very important fact. You know, you could license the ARM architecture, which means that we get the RTL code, we know what is inside, we can modify it, we can adapt it, we can create very efficient modified version, but we have a whole ecosystem out there already. We have applications that were ported to ARM architecture. We had almost the whole software stack not completely prepared that you just copy and paste it, but you know, you have quite a few things already developed which can give you results in a couple of years time frame. So you focus on the architecture, you focus on the underlying system, and you have on the global level, you have the large ecosystems of users that are already familiar and are already developing for ARM. So for us, it was one of the major decision points at the beginning saying, yes, we want something in the near term. So we decided, yes, okay, we are going to go with the ARM architecture. But in parallel, we would like to develop something completely European, I would say, without licensing. So the decision was that, you know, RISC-V was at that time starting. It was very promising ISA without any licensing issues and legal issues, which is, I would say, the most crucial point in the selection of this. But RISC-V is, as I said, ISA, instruction set architecture. So it's nothing more than just a list of some instructions, not actual design. No, just instructions and how they're supposed to work. How are you going to implement that in silicon? It's up to you. So, and we knew from the very beginning that this process is going to take longer. But if we manage to develop an efficient processor families that are based on RISC-V, we have here really an important advantage that you don't have to license anything from anyone anymore, and that you can independently develop really new category of processors on the market. So these two design choices were kind of, I would say, crucial in the very beginning, in the very first phase, before EPI even started, in the preparation phase. Those two things were decided at the very beginning and said, okay, yes, we are going to try to do this and develop processors based on that. I will try right now, I mean, this was the reasoning why we said why ARM and why RISC-V. So I hope that this at least clears a little bit the information that you might read in internet or in some papers, or see in some conferences about EPI, and you have the ARM side, you have the RISC-V side. Now you're questioning yourself, okay, but you said that you want to develop your own processors. Why did you have two different ones? This was the major reasoning behind it. So what is the current status? Developing a processor is for the first time in Europe. So it's not like you did already 100 versions in the past. You have, I don't know, 10,000 engineers that did that already, so you just develop a new one. No, we have to, start from very beginning. It's a very complex process. First, we need to attract engineers that are familiar at least with the process and that have done that in the past, probably with some other companies that are out there. And because, as I said, European HPC processor design was not existing, so you had to really collect pool of smart people and smart talents like you are here, and try to bring them into the project and try to start something new. Second thing is, unfortunately, and we all know that, I learned from Alejandro that here we have a lot of people that deal with hardware. As hardware guys, you know that software is so easy to modify. If you made an error, you have to find it, you recompile it, you send out the new version. With hardware, well, it's not that easy. I mean, you find an error, you have to find the money to build a new component, then you have to somehow replace it in the device if possible. So it's an expensive trial and error process. So, and also because of that, we were having, quite challenging times trying to reach to our goals. I will now try to give you the status of the two processor families that I told you about. So right now, after DPI finished, so what did we do? Are we okay? Are we not okay? Did we do good? Did we just spend money for no reason? I think that we did quite good given the circumstances. Let me give you the first half of the processor families. REA. REA is the ARM general purpose processor. REA is a commercial name of this processor family by CPERL. It is currently the most complex processor ever designed in Europe. So what is REA? on this slide, it gives you, I don't know if you can see it, you know, from the audience, but this slide, this is kind of like, I would say, the most important information about this processor, what it is. It has 80 ARM Neoverse V1 cores. It has billions of equivalent gates, transistors. I don't want to go into like how many layers of this and that it has because, you know, it's, as I said, very complex technology that you have to adapt. What is important to have is that it has HBM and DDR in the same time, which is based on our analysis of application, an important factor that could enhance the performance of the core, being able to provide the data faster to the processor core. Because you can have fantastic core, if you cannot feed it fast enough with the data, then you basically lose all of the advantages. So in the REA 1, we decided to have both HBM and DDR. And as you see, it's you know, packaged, and what I can happily say, it was manufactured in TSMC. Again, one of the questions that I often get is, okay, you want to have European processor, so where are you manufacturing that processor? Unfortunately, as I mentioned earlier, today in Europe there are no foundries that can really produce this type of technology. Hopefully, with the CHIPS JU activities that I mentioned earlier, we will move towards that in the near future. But right now, REA was taped out by TSMC in Taiwan. And what is important to mention is that around these days, and I mean these days, next few days, we are expecting REA to come back from manufacturing, which was a long process. It was supposed to happen earlier, but as I said, you know, designing this complex processor for the first time, it's not an easy task. And it's also not a cheap technological achievement, because people had also to find financing for tape out, for, you know, all of the things that you need for, you know, designing such a tape, such a tools, you know, verification equipment and everything else. But we are happy that we will have REA right now as a commercial processor out on the market. What are some of the advantages of REA? First of all, let me, you know, just, you know, come back to this slide. What you'll be, maybe what you saw here is it's manufactured in 6 nanometer TSMC process, which is today not the most advanced process. We understand that, but at the time we were discussing with TSMC, you know, the production of this was really state-of-the-art technology. And in the meantime, with, you know, some of the design challenges, with, you know, some of the, you know, accessing foundry challenges and everything, we had really to keep up with this initial decision, but the next processor will be in the state-of-the-art version, the next version of the processor. What are the basic advantages of this processor? It's, of course, it's designed for high-performance computing, so high performance, of course. And as I said, inclusion of HBM is, of course, one of the important things. Neoverse V1 core, it's very efficient ARM core that adds to this. It's energy efficient. So we can, kind of say that, it was from the very beginning designed to be energy efficient. And of course, what I mentioned as well is we developed together with ARM the whole ecosystem that is needed, the software stack that is needed for usage of this processor. Now, to go beyond what we have today is, REA was our first product. So this is the processor that we'll have as a first commercial product, but this is just the start of the, I would say, the nice technological story. With that, we covered, I would say, the most difficult part is to get people that know how to design this, to go through the whole process, to find money to actually produce the chip, to get it out there on the market, and to test it. So basically, this is the most difficult part. The second version is much easier to do because you have all of these steps already more or less in place. Now we have to think about, okay, what is the market? What could be the different versions that we could provide? But, this is much easier than starting from zero that we had in the beginning. So a new processor family will be called Athena. Athena is a kind of processor that is designed for dual use, which means that it can be used in standard kind of commercial applications, but it can be used also for some space, military, other type of applications that are, I would say, unfortunately in these challenging times, very much needed. Why is this important? What is the difference between Athena and REA 1? First of all, both of these devices have European technology, which means that we do have the RTL. We know all of the details of the processor. And why is that important? Because in certain strategic applications, you want to be sure that there are no hidden parts of the design that you are not aware of, like kill switches, like backdoors, and here we know what is behind the design. So this is an important part. Second thing is REA is designed to have very large number of cores. Sometimes, for example, when you look at the edge HPC, maybe you don't need that many cores. Maybe you need smaller devices. So Athena will be able to basically provide a various kind of sizes of the chip with different number of cores, which can then adapt on the market for the applications that are not really high end. Next thing that is also important is new packaging. So REA processor requires a socket. And the design with socket is, again, more expensive version compared to the chip that can be soldered. So Athena will also have this option, which is like less expensive packaging. No HBM. HBM brings a lot of cost to design, and sometimes, as I said, in certain application areas, you really don't need HBM and the costs associated to the HBM. So it brings really completely new business perspective for this architecture with the architectural knowledge that we gained from designing the REA, which is more complex and with many more features. And as I said, dual use is one of the important markets today. Of course, our major market is still, performance computing, but these dual use markets are very, very important today. When is this chip targeted to be present is second quarter of next year, which, we can say that, this is very short time frame compared to, of course, initial development that we had in the beginning. Also, one of the things that we, from evaluating the market, that we found out is that the chiplet market will become predominant market probably in the future. Now, what is the idea behind chiplets? As you probably know, if you want to, let's say, have more powerful processors, what you can do is get more cores. But if you want to have more cores on a single die, it gets your manufacturing more expensive. Why? Because of the area of the die is larger and larger, yield is getting lower, the costs are going up, so you cannot really expand this too much. But if you take approach of having number of dies that you connect together, then you can have, for example, many more cores with less expensive individual dies that can give you the processing power that you need, but that are kind of financially more attractive. What you also get with that is that you have a number of companies, it could be SMEs even, or mid-sized companies that have their own designs, right? They have their own accelerators for certain markets, but they don't want to go into the whole process that we went through of designing the general purpose processor, because it's an expensive thing. So what is solution for that? It's the actual win-win. I know that this is a kind of a buzzword, but it's really a win-win situation, because what you can provide is you can provide the general purpose core in a chiplet, and then they can have their own chiplet that does some other processing. And for them, it's cheaper to buy this already finished system that is manufactured in volume than develop their own. Because maybe they don't have the volume, maybe they don't have the actual design power to make this. So this is a very attractive future business case that we see that is already taking, I would say, a lot of ideas in industry. So you can combine different chiplets to get more power, or different chiplets to get different accelerators together with general purpose processor, and make the combination that is really efficient, both from processing side, both from business side, or from efficiency. Okay. The second part, equally important, is the accelerator. As I said, in the very beginning, we decided for the accelerator part that we will go with the RISC-V ISA. So what we did is, at the beginning, in our consortia, we identified several, I would say, important acceleration areas where many of the applications that are running on those large HPC systems are needing, that we can develop using RISC-V and enable more efficient and faster execution of those applications. So right now, this slide is a list of, I would say, key IPs that we developed on this RISC-V side. And what you can also see in articles and in news press releases, we named it EUPEC, European Accelerator Chip. So EUPEC, we taped out already 2 versions of the chip. So it was version 1.0 and it was version 1.5. Not to kind of misunderstand, these were not huge devices, very complex devices like RIA, but these were smaller devices that were primarily used to test, some of the architectural decisions that we did. And of course, they were taped out in technology that is less expensive. So for the second version of the chip, we named it version 1.5. We use 22 nanometer technology, and it was manufactured and returned in 2023 to the consortium. In that chip, we had several cores. I have that here on my slide. I'll give you just some information on each of those. First is the vector core, or vector tile within the chip, which was a RISC-V core especially designed to enhance vector operations. Now, what you can say, of course, is, okay, vector operations are known already in many processors that are out there. Well, one of our design choices was to go with the very large vectors. And when I say very large vectors, we are looking at 256 double precision element vectors. So this is significantly larger than the vector sizes that you have in the current architectures. We have tried, some of our partners that are on a daily basis running the application on those big systems have tried in simulations. This is how we came up with this, of course. They have tried some of those big applications, and they proved to be, these vector sizes, they proved to be very efficient for many of those large applications. So this kind of acceleration could be really beneficial for those. Again, what you have also seen today, especially in the AI domain, is variable precision computations. So not the precision with, kind of standard 32 bits or 64 bits elements, but, algorithms that use the opportunity to have different precisions. So we have also developed, based on RISC-V, so-called VRP processor and tile. And also we have designed the accelerator for stencil and tensor operations, also that efficiently handle some of the typical operations that you can find in a number of large applications. Beside those three basic processing tiles, we had several additional tiles that kind of create the whole SoC. So we have the L2 home node and, of course, NOC and SerDes IPs that were also developed within this chip, because when you take a look at the actual processor design, the cost of the additional IP is also not only the processing core, but the NOC itself, all of the peripherals that connect to outside devices are also important and build on the cost of the chip itself. So if you have your own technology that you can use for that, that reduces the need to license something like that from third parties. And here is just a basic diagram of those tiles in our EUPEX chip. So as you can see, we had only a couple of tiles of each of those processors and all those IPs. And what we used was to kind of reduce the cost of the processing itself is we tried to use the FPGAs for some of the communicational part and for the memory part of the system. So basically what you can see here is the EPAC, and then here is the FPGA that has all of the interfaces and memory. We didn't want to basically build the memory on the chip to make it less expensive to manufacture. And here I have a couple of pictures that show EPAC chip in the actual setup. So we have here the chip. We have a special board, the daughter card that we developed, basically where we plug the chip in the socket. And then we plug that to FPGA board that then serves as a kind of like home for this EPAC chip, and where we were able to test it. And on this slide, one of the initial slides when the successful Linux boot was done, and I know that guys that were doing that were very happy that night when for the first time it really booted without any problems. Right now we are far away from that. We are running really complex application on this system. Of course, this is a very small setup right now, but the actual system is efficiently working. Now, as I compare this, same thing in the ARM part, let me tell you also what is new coming with the RISC-V part. So we have planned also additional tape-outs for the EPAC, and this is within one of those projects that I mentioned, one of those pilots, EUPILOTs. So we have planned another tape-out of the vector chip, right now with some modifications and more number of cores. And we have also planned another separate tape-out of machine learning and stencil accelerator cores. And this one is going to be really taped out in quite advanced technology, but again, only as a test chip, as a kind of like a prototype as well. Now, with that, I gave you kind of an overview of the two architectures. I would like to use this opportunity just to, kind of give you maybe a little bit of something that was developed within my group. We did a number of things in this project, but one of the things that we are kind of proud of is the design of RISC-V vector floating point unit. We named it Faust, and the main feature of this floating point unit was that it was really optimized to vector processing in EPAC chips. But it's not only in EPAC, it can work with any RISC-V design today or in the future. One thing that led to another, we improved it over time. So here are some of the basic features of these chips. So we support standard formats. We also support expansion to some of the newer formats that could be customized, especially, as I said, for AI. Some of the formats are not the standard ones. We can easily adapt the design to some of the IEEE-like formats that exist to the market. And what was especially important was the rounding up modes, because as you know, in many operations, the way you round up some of the results of the operations are very tricky, and there are different ways how you can do some things. So you have out there some of the devices that are not compliant to some of the standards that define this operation. So we modified our design to be fully compliant with both IEEE and RISC-V definitions of computation. What are from the design perspective, what are some of the main features is what we have seen. I mean, when you consider designing any digital design, including a processor, you think, okay, you create some Verilog code, you synthesize that, you get some good result. You put some options, it gives you best result possible. Well, not really. So from the experience, just to give you an experience, for example, we played to reach some of the frequency, some of the target frequency, and then we realized that, you know, for example, design was working with higher frequency, but was not working with lower frequency. You would kind of expect the opposite, right? Then you give it again to synthesis tools, you know, it gives you weird results. You know, you kind of reduced in your RTL, you reduce some things, you get larger area. Well, it should be, again, the opposite, right? So basically, you should not trust the tools 100%. I mean, the tools do their job. But if you want to really nail it down to be as efficient, as you know, fast, or you know, reduce the area to maximum, you cannot rely only on the synthesis tools and on the optimization tools. We have learned that also with, for example, trying to create pipeline stages. So, for example, in order to match the data coming from the vector unit, we said, okay, we'll need, I'll give you a concrete example, 5 pipeline stages. But then, you know, we learned in different setups and everything, we tried to optimize the logic between those pipeline stages. And then you see that the tool is doing weird things. You know, it's kind of like moving registers so that you have like 3 stages, one behind another with almost no logic, then huge chunk of logic, and then 2 pipeline stages. Well, it's everything but not optimal, right? I mean, we all learned probably in the basic computer architecture that if you have pipeline, you should try to get the kind of like the logic, you know, in those stages kind of be timely equivalent, right? Not to put like big chunk in the middle. So we did a lot of hand optimization on that and you know, try to make it work. And we do have some know-how that we can optimize the pipeline logic of this floating point design so that it can work with different number of stages, different target frequencies, or you know, we can remove some of the unneeded logic. For example, if you don't need, I don't know, square root operation or division or something in your processor, we can get it out and get the more efficient design or similar things. Yeah, we, of course, support all the standard RISC-V operations that are defined in the standard. I don't want to go to that. And this is kind of like a basic diagram of top level of the floating point unit. What you can see here is that, for example, you know, those 3 blocks are pipelined. For division square root, you probably know that if you want to implement it in hardware, it's usually an iterative process because it's more efficient area-wise. Of course, I mean, you can do it linearly, but then it takes a lot of area. So we have the option, you know, based on the target frequency, how we can, you know, get this either faster or less requirement for the area. Another important thing is with the design, once you design it, you want to be sure that this is actually working as it's supposed to work. Because again, tools are not 100% ideal. So you try to verify your design post-layout or post-synthesis. So we also defined UVM-based environment for testing on design that, of course, addresses all of the specifications that are required. And we named this tool Fever. And we used it, you know, during the design, and it can be used, of course, to test either Faust or any other FPU that you would like. test. And we have right now at this moment, also I would like to give you state of the art, we have advanced version of Faust and Fever that are really highly configurable and that have advanced options. And we have just, a couple of months released version 2.0 with number of both algorithmic and architectural choices that you can select based on your requirements of the design. Also for that, we created another spin-off, another small company that is right now taking this to the market. So again, if any of you are going to design RISC-V or any other similar processor that uses floating point unit, and if you need that, you can contact Proactive Compute company that was also spin-off from EPI, trying to build that IP to the market. Okay, I have covered pretty much all of the technology from EPI. I would like to go again, maybe on a little bit higher level to see what are the outcomes. Here is the roadmap. This is, as I said, how we all started. We are here right now. So we have REA-1 chip that is coming out from manufacturing. We have already finished design of the REA-2 chip. The REA-2 chip is the next generation of REA-1, which will have more cores. It will be designed in a more advanced node, and it will provide really higher efficiency than REA-1. We have also started our new RISC-V chips, that will be taped out. But also I would like to show some of the industrial use of our devices. As we said in the very beginning, RISC-V takes a little bit longer to reach the commercial levels. So right now we don't have commercial version of RISC-V chips yet. We are going to have it. I will show you in next couple of slides. But with REA, we have some products and we have first customers. For REA, our first customers is going to be European Exascale system that is built part of the Jülich Supercomputing Center in Germany. So Jupiter is most advanced supercomputer in Europe right now. It's currently being built. It's the major processing part of Jupiter is universal cluster and GPU booster. Of course, because REA is just coming out, we cannot expect this whole system will be built only on REA, but the cluster module will utilize REA-1 chips, and this is going to be actually in full use in a Jupiter system. The cluster model will have something more than 1,000 nodes. As I said, it will use also REA-1 with HBM. As I said, the HBM part of the design is very important for some of the applications that require higher data bandwidth. And those REA chips will be included in the nodes that are in Bull-Sequana XH3000 system designed by Bull. It was initially Atos, then it was Eviden, now it's Bull again. So again, Bull was part of the EPI consortia also from the very beginning. So in the same time we were designing processors, they were designing the systems. So the servers that will actually have those where you can plug in your processor and have the whole system ready. So this XH3000 system by Bull was also partially designed as a part of EPI processor. In another commercial use of this processor will be in the next largest European exascale system, which is Alice Recoque, which is going to be built in France. This is going to be a supercomputer that will replace CEA's current supercomputer and will be kind of 50 times more efficient than the current one, and it will require only 5 times more power than the current system. So energy efficiency is really, as I said in the very beginning, one of the crucial design decisions that were important. Also, this system is going to provide significant resources for Europe's AI factories, which I know that everybody of you today, if you don't mention AI, it's not a good presentation. So today AI is really big also in research and industry community. So this system is also going to, of course, enable some of the AI factories that enable future development of AI. And this Alice Recoque supercomputer will have CPL's RIA-2 processors. And this is kind of the setup of the system, which is fairly unusual, how the system will look like. It will be, the installment will start this year, but it will finalize in 2027. Now, with RIA, I think that I pretty much completed the whole history from starting the design until the commercial products that we already have. Now, with the RISC-V part, what I said is that we do not have the actual RISC-V commercial components on the market right now. So one of the, again, strategical decisions was that EPI is followed by another project that will exactly bring that. So right now with EPI, we did some initial development of RISC-V ecosystem. Now, guys, let's bring it to the market. So there is another project which is called DARE, or Digital Autonomy with RISC-V in Europe. And the basic idea behind DARE is exactly that. Okay, using the RISC-V technology, create the processor that are going to be commercially competitive on the market. I will give you an overview of that. Just to let you know, their project started just a year ago. So it's brand new project. So we don't have too many results today because it all just started. It's a very large consortia, well, not even, but significantly larger than EPI. So in order to get all of these things really moving and producing things, it will take some time. But again, it's planned as a two phases of 3 years. So we expect by the end of the second phase to have exactly what we said, commercial RISC-V European chips. So what is there about? Again, the idea of RISC-V ISA as an open standard is the core of the DARE project. Second thing is, again, what I mentioned earlier, chiplets as a very attractive technology to be used in the future. So chiplet technology is is also very important to be part of it, so we should design RISC-V based chiplets. And of course, we can use as much as possible the open source software ecosystem for that. In there, we have 3 major chiplets or processors. One is the vector accelerator. I said this is continuation of EPI. So the importance of vector processing was already recognized in EPI. So this is a continuation where we said, okay, now bring this vector processing, vector acceleration to the market. Second thing is AI processing acceleration. So in last 10 years, AI became very important. So it was recognized that the AI acceleration should also be, kind of part of this, their project. And there is, of course, the need for general purpose processor, which is also based on RISC-V. Together with that, I don't want to repeat myself, processors are not the only thing. You need the whole software stack around it. And here is something that is very important. With ARM, you had already a lot of things developed. With the RISC-V, it's a growing community. So still, a lot of things need to be developed. They're not there yet. So a lot of things within this really need to be developed by the consortia and, of course, by a cooperation of different partners around the globe. Co-design is an important thing here as well. So analyzing the application to give you some of the design parameters, having some of the kind of first architectural choices, providing to application developers to optimize their codes. So continuous co-design processes, again, very important. Here, another slide of what is there or who is there. Again, there is a large consortia. Here are the list of the partners. Of course, I don't want to go through this. You'll have it in the presentation. And I can just give you a short overview of the architecture itself. So for the vector processor, as we can see, it's very similar to initial idea that we developed in the EPI. So we have large vectors that are designed within the VPU, and then you have some general vector core that is basically controlling the vector unit. Then you have in a chiplet, you have number of cores with, we are targeting, some of the L3 caches also here. Then you build that on SIP, and then you put it on some initial PCB. The form factor here as a PCI card is just, kind of for visual identity. Not necessarily will have all of the cards developed as a PCI cards. We might have also other type of solutions. Because I already talked a little bit of vector previously, let me move quickly to the next core, which is AI core. So the Accelerators AI core is very unique design because it uses in-memory computing for the acceleration of the algorithms. So it's very specific type of design. It's not standard, processor. You do something in your core, but you have also some processing. I mean, you know what in-memory computing is as a principle. So basically, you do a lot of operations in memory, so you don't have that overhead of bringing the data in the processor and then storing it back. But you do a lot of processing in memory, and this is where we see a lot of potential for many of the AI algorithms. And of course, general purpose processor is going to feed the AI core with the data. And general purpose processor is, again, RISC-V based. As an initial goal of the first 2 years is we are going to build a prototype that will have just some prototype devices. And we will integrate those devices. And, here we have, I don't want to really read to this list, and all of the processes that are needed to get the chips from designing the processor, physical design, PCB design, bring up the boards, building the prototype, building the nodes, connecting it with a memory with other nodes, and then building the machine with that and trying to test and run the applications on this type of prototype. So when I mention applications, we have selected several large applications to use as a vehicle for both evaluation and co-design. Here is, the list of the application. What they do is we have, of course, weather prediction, some of the ocean modeling, biomolecular simulation. They're all very large-scale applications. They're not like small kernels. They're, very large applications that use enormous amount of resources, which is exactly what we need to evaluate this kind of architecture. And here you can see, which application will be testing that and co-designed with different type of cores in our system. And of course, some of the notes on the application itself of, for example, what kind of programming language they use or different algorithms they use. To give you a complexity of software stack, I actually very much like this slide because basically you need all of this. So, and if you have an architecture that is already there for decades, then it's easy because somebody developed it some time ago in the past. When you have new architectures, then it's not that easy because maybe there is something out there, but you're not sure if it actually works well or if it's efficient enough or if it's there at all. So basically within this project, we have very demanding task of providing all of this software stack because without it, as I said, processors really don't make sense if you don't have this software support on top of that. And, we are trying to envision that we will test in the first phase, that we will test some of the applications that I mentioned earlier on some of those either vector or AI accelerators on some of the preliminary boards and try to see, if it actually brings some advantage in the design. Of course, in the next stage, this is the first stage. In the next stage, this is not going to, this is right now going to have some standard hosts. But at the next stage, the general purpose processor will have basically this host functionality that right now we are using from some other systems to verify just the design. That we will, not right now, we are, as I said, in the first year of the project. And I can never say enough how application guys and hardware guys have to talk to each other all the time, because it's very important. I know people that develop applications that would love that they don't have to change anything, right? Just kind of rebuild. But unfortunately, it doesn't work like that. You need to put some effort into trying to optimize maybe some basic kernels to the new architecture to use the features of the new processor that you have. Also, on the hardware side, you would like to build your new processor, and then you would like that, it works perfectly in some application areas. Well, it doesn't work like that as well. You need, when you're designing the processor, you need to talk to the application guys and try, okay, these are the most important things. Okay, if you can select one or two things that you can implement, then you pick ones that will bring, more effect to the application. So this co-design process is at the core of collaboration of many of our partners to both have efficient processors and efficient applications later on. And, of course, here is a small recap of the 3 processor cores and the software stack and, as I said, hardware co-design, and hopefully, really, sovereign European hardware processor ecosystem. And with that, I would like to finish my presentation today. I hope that you survived. And I have, eventually, if you're not too tired, I have a couple of slides for students. If you would like me to share, for example, for what some of my students are right now doing, undergrad students. Leo, who was here, he was in Zagreb for a semester last year, and we were happy to have him. And there are also some opportunities for some of you maybe to come to exchange and to come and work with us. And if you allow me, before going to relaxed conversation, I can just briefly. I have some slides on this, but I think that you had enough slides for today. So, but we are trying to build an open source RISC-V course designed by students. So basically, very simple design, system Verilog with implementation in FPGA, so no fancy and expensive setup. We would like to expand that with new instructions. We have a number of ideas what we can add to this processor core, but my major goal is that my students do that by themselves, right? So they have to work on that, they have to see the errors, they have to try to find out how to fix those errors, make it work, and then, maybe Leo can tell you, he's here with you. They're happy when they come. I love Fridays with good news. This is my, I say to my students, okay, on Fridays, come back, to the meeting that we have on Friday with some good news, then I'll have a great weekend. If you don't have good news, keep it for Monday. So on Fridays, we usually have meetings when we meet, they try to tell me, okay, what new they did well, and then on Monday, we set up new tasks and what we do. We not only try to do that, we have some of the software part of the application as well. Of course, I know that for students, AI is very interesting. So we are trying to use some of the AI inference. We would try to optimize some of the AI inference implementations so that you don't have to compile those huge software packages that you can find out there that do everything for you. But sometimes if you want to actually implement that in the real world, it's not as efficient. So we identified certain kernels that we say, okay, how can we optimize those kernels on RISC-V to run as fast as possible? And that will enable the application later on to run faster. And we have also interfaced that with some of the imaging and video applications, because in number of key applications like smart cities. You have a lot of cameras out there that analyze what is happening in the surrounding. Today, to transfer that data to some data center and process that there is not very efficient, because you send a lot of data there while you need only extraction of information. So you have a lot of edge processing where basically you try to do some initial processing on the edge. So for example, where the camera is, and then you just send some basic information to some higher node where you do something with it. Also, for example, in automotive application, an important segment where there's a lot of AI going on, you have a lot of cameras, radars, lidars. You want to do everything very smart, but the car is still a car. You cannot put a server in a car. So you have to do very efficient processing in a car. So one of our things is try to merge this AI and imaging processing and try to kind of play a little bit with how to optimize that, how to do some even assembly level kernels on RISC-V, so you can run some things faster. So as I said, I have a set of slides with that, but that will be maybe just too much for you. I should? Oh, okay. If you want. All right. Okay. Okay, well, I have time. Okay, this is HPC architectural application is my research center where I work. So as I said, we do a lot of architectural stuff on the processors, but we do not too much of the software part. So not the software stack. My group is not really working on that, but on the application part, we do a lot of that. So this is our RISC-V processor. Why the name RISC-V? It's FAIR, my institution, like Faculty of Electrical Engineering, like F is from FAIR, and then RISC-V, so we called it RISC-V. We had 3 previous versions, RISC-1, RISC-2, RISC-3, that were with our own instruction set, and then a couple of years ago I decided, well, RISC-V is kind of interesting, let's move to RISC-V instruction set. So we named it, we skipped 4, we went directly to 5. This is, just a, kind of basic diagram. We have like 5 stages, 5 standard stages of the RISC-V. We have some, instruction and memory, instruction and data memory interfaces, that we have implemented. We have also implemented the XE protocol to communicate with other devices. Well, when I say we, I should not say we. I should say they, students. They implemented that. They use standard Xilinx tools. System Verilog is by default our design language that we use, and we use some of the low-cost Xilinx reference boards because the logic is really not that huge, so we can use really those low-cost boards. And here is one example. So here is the pink board, which is this low-cost Xilinx board that we use. This is stupid board. I mean, this is just board that has a lot of peripherals, like 7-segment displays, some switches, some push buttons, So basically a lot of peripherals so that we don't have to solder different things. And this is again our even dumber board, which is just a connection board. So connect those two because, I mean, otherwise you have to connect it with cables, and then, with cables, how it is, now it works, then next minute it doesn't work. So this is, for my students, this is a kind of basic setup for the development. Again, on the application domain, I said AI and imaging in video. Bolt 65 is our own implementation of AJVC video coding algorithm, and Jaguar is our own implementation of JPEG imaging algorithm. And as I said, we use that in typical applications that we find today, which is, I don't know, a collection of videos or images and then processing that into some network. Maybe a little bit about this Bolt 65 suite. Some of the things that we did with that was transcoding. I don't know how many of you know what the transcoding is, but basically the process of where when you take a video, you have it in one resolution and with certain frame rate, for example. But many times you would like to replay that with other different resolution or different frame rate. And this is where the problem is. Because if you have, for example, HD video, you want to play it on your little device, then you have huge amount of data going to a device that cannot basically show it. So it doesn't make sense to use it. So the straightforward method is, okay, you have this compressed data, you decompress it, and then you again compress it into some smaller video, which is completely inefficient process. It's very demanding. I mean, video is one of the most demanding applications that are out there today. So transcoding, what transcoding does, and you see it every day in YouTube. So what it does, it basically does a lot of things on the server side. So it does not decompress and recompress things, but it uses some of the compression algorithm choices. So it stays in frequency domain if it can. It stays in frequency domain. It reduces some things in frequency domain, so you don't have to do that much processing, and you can get your output with significantly lower processing. And that requires, for example, discrete cosine transform is a typical math algorithm that uses most of the processing time. So if you can, for example, implement DCT efficiently in your hardware, you can reduce this processing time quite a lot. There are, of course, some other kernels that are important, but just for example, DCT is one of them. So analyzing this process and analyzing what are the most demanding kernels and how you can efficiently implement it on this processor is one of the things on the software side that we did for both video and imaging. And for imaging, this is, for example, one of the applications that we did as a part of EPI at the very beginning, automotive application. This was an actual BMW test car. And the reason why we have used our algorithm there and why BMW used this algorithm is they had a lot of cameras, but cameras were basically producing JPEG images, so not videos, they were producing images. But as you know, JPEG is compressed format. If you want to process it, you cannot process the compressed format. You have to decompress it, and then on the raw image, you do whatever you want to do, right? You extract some objects or something like that. But this decompression is expensive in cars. If you have a lot of cameras, today you have, you Google, you have zillion algorithms out there and open source libraries that do JPEG compression and decompression. The only thing is they are not efficient. Well, let me get that back. Most of them are not that efficient. There are some that are very efficient. But if you want to just grab one of those libraries, include it in your project, it might not be that efficient. Why? Because JPEG standard has enormous set of options. Usually those libraries support most of those options, which results in the complex code, because they expect that you want to use option A and B and C and D and E and F, and then you have large code. Well, if you have your camera, you know exactly in the car what the camera produces. It doesn't play with the options, right? It gives always the same compressed format. So you can reduce a lot of things. And if you can optimize those critical kernels, well, it runs on very little portion of the processing time. This is exactly what we did. So we basically used our JPEG decompression and all the algorithm, but it was efficient. And then we fed that into the AI algorithm that was detecting some of the objects. And we actually placed that as a test. I mean, this is our system, but it had the early version of the RISC-V version, processor version, together with that in a trunk of the it was running in German roads and analyzing things. And about the AI networks and optimizations that I mentioned, so this is a typical diagrams that you will see that you have in almost all AI networks. And when you closely look at that, then this is on the left side, this is what is important. These are some of the basic kernels. And basic kernels are, addition, multiplication, some of the basic functions. So basically what I give to my students, okay, you pick one of those functions, you focus on that functions and try to implement it as efficient as possible on our core. So either on the vector core, on the general RISC-V core, and we play with that. Okay, so this was my additional couple of slides. And with this, another word that I know in Spanish, gracias. And of course, I'm open for questions if you have.
Ahí está. ¿Están vivos? ¿Sí? Levanten la mano derecha, por favor. Ah, ok. Están bien. ¿Alguna pregunta? Dale.
Hola, se escucha. I would like to ask if you are planning to introduce in the EPI project an extension in the processors to do virtualization or something like that.
The acceleration of the virtualization.
Not the acceleration, as an extension for doing processing, maybe containers or something like that. If you think that it was needed in the future or for a particular application.
I would say absolutely yes. I mean, it's beyond EPI. EPI is over, but more there and continuation of there. We are looking at different types of accelerations in the FAST. And one of the things that I mentioned, this co-design, is very important. If we find that among the applications that are running on those systems, there is certain type of acceleration that will be very beneficial, the whole idea of the chiplet approach is, yes, let's build another chiplet for this kind of acceleration and add it to those that are already there, because it's, as I said earlier, it's from design perspective, it's very efficient. And then also from the industrial perspective, you can play with the different chiplets to target different applications. So for example, for one application, you need more of these types of chiplets. For the other one, you mix with those. So yes, that's the chiplet approach is basic idea behind exactly what you're saying.
Thank you, thank you.
Hi. So I have a few questions, but
sure,
you can stop me when you want. Regarding the launch of Athena and Real, that you are targeting for the next year.
Right.
And I wonder if you have the processor design, but like the motherboard, I mean, no? You want to go to the market, and you need the surrounding hardware.
Absolutely.
So you didn't say anything about that.
I did.
Okay.
The Bull.
The
Bull motherboard, the Bull systems. Yeah. This is actually the servers are built by Bull. I mean, I'm sorry if you don't know. I mean, they changed the name 3 times in the last couple of years. First, it was Atos, and Atos was, the large integrator that exactly is building the PCBs, the server PCBs where we plug in. But then, they changed to Eviden, and right now, recently, in the last couple of months, they changed to Bull again. So yes, this is, one of the European integrators, but different ones like HP or somebody else is also our target eventually. Of course, whoever is building the servers where we can plug in, our processors are interesting for us. Yes.
Okay. And no sé si Okay, so another question, but it's more like a curiosity. You show a setup where you had a FPGA with a BCU 128,
right,
connected to your prototype.
Right.
I wonder if you already have the processor and some board where you place it, where you, why do you need the FPGA there? So what is providing you the FPGA there, the FPGA setup? The testing, what testing are you doing to your hardware?
I'm sorry, who is providing was with...
Can you go to the picture and saying, perhaps?
Yes, I will do that. This one?
This one, yeah. So here, what kind of test do you do to your prototype in order to validate your design here in this part?
We were running the operating system. We were running the applications on top of that. The only thing is that it was running slow. Because, first of all, our processors were not running, at a super high speed. Second, you don't have so many cores that you can use. So basically, the only thing with this setup was, okay, we start an application to see if the processor is working well, but it takes forever, for complex operation to finish. I mean, some small kernels, you can do on a kind of daily basis, but some of the bigger applications really, take a long time. So this is a limitation of this kind of setup.
Okay.
No, thank you.
Hi. I'm not sure if I understand correctly. The chiplet approach is like you have the modules like the general purpose, some accelerator, and you can produce a single chip on demand on the same die.
No.
No?
No, each chiplet is a separate die, right? And then you combine those chiplet on SAP, which is kind of interposer package, right? So basically kind of like do the Lego style combination of several chiplets, but the individual chiplets are less expensive to produce, and then you can combine different types of chiplets. They don't have to be exactly the same types, but the final chip itself has an interposer that combines chiplets. You can add usually on that some memory, and then this becomes your chip that you plug into your server board.
Oh, I understand now. Thanks.
You're welcome.
Hello, how are you? When you were talking about the Athenia project, you talk about it can be used for IE, IA, Cipher, and defense. How can it be used for Cipher applications or defense applications?
For example, one of the things that is important is those types of application is reliability. For example, if you solder a processor on the board compared to having it in a socket, it's much more resistant to vibrations and different physical things. We are trying also to test it for radiation, so that, for example, if you put it in some of the space application, sensitivity to radiation is one of the crucial things. It's not intended to be for mission critical parts of design, but more for data processing part of design. Usually, if you talk, for example, in satellites, you have kind of mission critical systems that are really hardened significantly so that they are 100% reliable. We do not target that. But apart from those mission critical systems, you have a lot of kind of processing systems where you can have, for example, redundancy, I don't know, triple redundancy or double redundancy, where you can do some computations without having those kind of special type of devices that are, of course, significantly more expensive.
Thank you.
You're welcome.
Good afternoon. So I get that the approach of the EPI project was to tackle on industry applications, but I was wondering if either further developments of the EPI chips or the DARE project are planning to tackle on the consumer grade market, especially now that Intel isn't as much of a beast as it was before.
Not really. I mean, for consumer market, it's a huge volume of chips that are required. And we understand that as, it would be maybe kind of attractive to go into that market, but it was not our goal. And still it's not. It's more high-end processing rather than consumer market. So the goal of these processors are not really for the consumer market.
Thank you.
I have one question, not technical. You mentioned the European Union participation in the project. We can imagine that it's a lot of money invested in this initiative. Approximately, you can tell us about the percent of participation of the European Union as public institution?
Yeah. No, I mean, it's public information. European Union is financing 50% of the project. So
50, ¿ok? Yeah. Cualquier parecido con la realidad. Eso quería. No, esa internal, same in Argentina. So, and another, you have done some power estimation when in the middle of design before the manufacturing,
Right.
and what I think that I have an idea, but can you tell us what software tools do you use?
I would be more than happy to tell you. I'm sorry, I don't know anything about this. You know, I was not working in this area, so I could make a wild guess, but it would not be, really useful.
Thank you. One more question regarding the EPAC 1.5 chip.
Okay.
You mentioned earlier that you have 256 vectors of double precision floating point.
Vector is 256
Yes.
double precision elements.
How many registers has the core of that kind?
A good question. Yeah, we have a special register set for these vector operations. What is the size of this register set? I would have to look it up. I don't know by hand, but yeah, there is a special register set for this.
An order of magnitude 1, 2, 10, 100.
I'm sorry?
An estimated order of magnitude, the quantity 10, 100 registers.
How many registers? I don't know.
You really don't know how much?
How many
How many?
registers?
Okay,
No,
okay.
I don't know.
Okay, thank you, thank you.
No, sorry. I can look it up right after this, and I will let you know.
¿Nada más? Hacemos una o dos más y ya lo liberamos, ¿sí?
Just maybe, I can pass around. This is the EPAC chip. If somebody wants to take a look at it.
Hi, good evening. I have a question about the part of the AI processing. At some point, what could be the limitation it could have? Because the way I see it, it could be that in some years, AI is going to be very involucrated in all the processing. So it could be possible that the major part of the processing could conduce to this part.
I'm sorry, can you repeat? I'm not sure that I understood the question. Sorry about this.
That the processors that are involved in the AI, no, this part could be evolutioned to a greater part of the chip. ¿A qué limitaciones podría llegar a tener la parte del procesamiento de IA?
¿Qué limitaciones?
Sí, porque como está medio a la mitad, no se podría llegar a ser un procesador más dedicado exactamente solo a IA.
He tried to ask about the limitations of the AI processing unit. He asked about the possibility to do a main processor dedicated to AI, only AI.
Okay, I'm sorry I didn't understand the question first. Well, if we are talking about this AI accelerator in there, the idea is that certain type of operations in processor are less efficient compared to those done in memory. And that's the whole focus. Right now, we try to do this kind of the old-fashioned way. We try to do the processing in a general core, whereas with this approach, we may have, with a smaller logic, with a cheaper design, we can have much more efficient processing using this completely different kind of computing approach. And that's the reasoning behind it. What you say is, can we do it in processor? Yes, we can. But we try to exploit this as a more efficient version than to trying to do it in a regular core.
Hello, good evening. You talked about that nowadays the RIA processor utility with TSMC in Taiwan, and you also talked about that in the future the idea is that you build it all sovereignly in Europe. Do you have any expectation on how many years you are going to have a factory that is going to be able to do this?
Yeah, very good question. Unfortunately, this is what we say beyond my pay grade. It's going to hopefully happen sometime soon. but you know, it's, as you probably know, the silicon foundries are extremely expensive. Europe is trying to build those foundries. Whether they're going to be available in X years from now, I cannot predict, really. I mean, I have the same question as you have, you know. Yes, and it's again, you said correctly, if you would like to be sovereign, you're producing it someplace else, it's not really ideal. Yeah, I agree.
It's the same thing that we talked about before the...
Yeah.
It's more important the engineering, but the manufacturing. The manufacturing is a commodity. You can manufacture in TSMC, but the important thing is the things that we put inside the IC. This provide from here, okay? De las malas clases van a ser en inglés, se los digo así. Okay. Okay, well, Mario, thank you so much. Excellent presentation. We are very proud to have you here. And you are invited when you want to come here.
If you allow me at the end, first of all, I was honored to have the opportunity to present here. I would like to repeat what I said in the beginning. Beyond what I explained here, I personally love Argentina. You know, I love, you know, coming here. I have some good friends here. If we can, you know, I have some students also here. If we can extend this cooperation, you know, beyond, I'll be, you know, really more than happy, so we can continue this discussion. And maybe just a little bit of something, you know, for all of you that came here today and then, you know, spared your 2 hours. I brought some giveaways here, you know, nothing special, you know, some little things that I would like for all of you just to, you know, take with you. I will get it from the bags, and, you know, please feel free to, you know, come here and take as many as you want. You have friends, you have colleagues, you have, I don't know, neighbors, you know, take some of that and, you know, sometimes maybe it will remind you on this presentation today. And again, I appreciate it very much. Thank you.